So this is a question from GATE 2018 from Chemical Engineering, question number 40. The elementary second order liquid phase reaction A plus B giving C plus D is carried out in an isothermal plug flow reactor of 2 meter cube volume. The inlet volumetric flow rate is 10 meter cube per hour. The initial concentrations of both A and B are 2 kilomole per meter cube and the rate constant is given as 2.5 meter cube per kilomole per hour. The percentage conversion of A is dash. So this is a question from ideal reactors part in chemical reaction engineering, and the reference NPTEL series can be found in module 1 lecture 14 design of plug flow reactors part 1 chemical reaction engineering 1 homogeneous reactors by Professor K. Krishnaya, Department of Chemical Engineering, IIT Madras. So here in this question, let us first represent the data given to us. So we have a PFR, and inside the PFR there are two reactants here which are A and B with initial concentration Ca0 is equal to 2 and Cb0 equal to 2. And the outlet will consist of Ca, Cb and the products Cc and Cd. Now the flow rate mu is given as 10 meter cube per hour and the volume of the reactor V is given as 2 meter cube. So using these data, we need to find the percentage conversion, which is XA in percentage. So what we can do here is we can start with the design equation of the PFR. So the design equation of PFR is basically tau is equal to V by nu, which is equal to integral minus dCA by minus RA from Ca0 to Ca. So here minus RA will be K Ca Cb, because in the question it is given that the reaction is a second order elementary liquid phase reaction. So minus Ra will be KCaCb. So we can substitute that in the design equation, and we also have the values for V and nu, which we can also substitute in the design equation. So if we rewrite the design equation, it will be 2 by 10 is equal to integral Ca0 to Ca minus dCA by K CaCb. So here we can note that inside the integration there are two concentration terms Ca and Cb. So let us see how we can deal with these two terms. So let us take a scenario. Let's say at time t equal to 0, we have the four elements, the two reactants and the two products. So at time t equal to 0, the concentration of A will be Ca0, which is 2, and concentration of B will be Cb0, which will be also 2. At time t equal to 0, since the reaction does not happen yet, the concentration of C and D will be 0. Now let's say at time t, where let's say our required fractional conversion has already happened. So that means, let's say X amount of reactants have reacted to form X amount of products. So the concentration of A at this time Ca will be equal to 2 minus X. And similarly, concentration of B will be equal to 2 minus X, because we just said that X moles of A and X moles of B will react. Because the stoichiometry of A and B are same, whatever amount of A is reacting, B will also react. So let's say if out of the 2 moles of A, 1 mole of A is reacting, then 1 mole of B will also react to form the products. So the concentration of A and concentration of B both will be 2 minus X after time t. And after time t, the moles of products will be X and X. That means X amount of C and X amount of D, or X moles of C and X moles of D will be formed after time t. So what we are trying to show from this balance is that once the reaction happens, or at time t, concentration of A is basically equal to concentration of B. So we can substitute this concept into our design equation. So in our design equation, we had 2 by 10 is equal to integral Ca0 to Ca minus dCA by KCACB. We can write the CACB as CA square itself, because CB is equal to CA as just what we have established so far. So this will be CA0 into CA minus dCA by KCA square. So this will be our new design equation with only CA term in our design equation. So now we can proceed easily and using the direct integration itself. So 2 by 10 will be equal to 1 by K. Integral of dCA by CA square will be minus 1 by CA, and applying the limits, it will be 1 by K into 1 by CA minus 1 by CA0. Also in the question, it is given that K is equal to 2.5. So substitute these values and just find the value of CA. So we have K is equal to 2.5. We also have CA0 is equal to 2. Substitute these values. We'll get 2 by 10 is equal to 1 by 2.5 into 1 by CA minus 1 by CA0, which will be 2. So rearranging this, 1 by 2 is equal to 1 by CA minus 1 by 2. Or in other words, CA will be equal to 1. So now we have CA is equal to 1. We also have CA0 is equal to 2. So the percentage conversion will be 1 minus CA by CA0 into 100%. And this will be 1 minus 1 by 2 into 100, which will be 0.5 into 100, or basically 50%. So the percentage conversion in this system is 50%.